Welcome to this explainer on piping design and drafting. Whether you're an aspiring mechanical engineer, an MEP professional, or a trainee in the oil and gas industry, we are treating our source material today as your absolute masterclass blueprint. We're going to break down the complex, heavy-duty industrial engineering concepts that literally keep the modern world flowing, taking you all the way from 2D drafting basics to real-world execution. So think about this for a second. How exactly do you map the veins and arteries of a massive industrial refinery? I mean, try to imagine the sheer mind-boggling complexity of connecting thousands of pipes in a gigantic process plant without making a single error. Because, let's be real, one wrong connection or one miscalculated pressure rating, and you don't just get a tiny leak. You're looking at a catastrophic system-wide failure. The engineers who solve this massive, high-stakes physical puzzle, those are piping designers. And today, we're going to learn exactly how they pull it off. Here is our roadmap for today. 1. Process plants and piping basics. 2. Industrial codes and standards. 3. Decoding PFDs and PNIDs. 4. Instruments, valves, and equipment. And 5. Isometrics and stress analysis. Section 1. Process plants and piping basics, the foundation. As a piping drafter, your work literally forms the critical infrastructure for massive process plants. We're talking oil and gas facilities, refineries, and petrochemical plants. You are the one responsible for understanding the fundamental materials that make these complex operations actually work. And that means you've got to know the different manufacturing types of pipes, and crucially, how to calculate pipe wall thickness. This is an absolute baseline engineering requirement. You can't just pick a pipe off a shelf, right? You have to mathematically ensure that its wall thickness can withstand the immense pressures and extreme temperatures of the specific chemicals flowing inside it. Section 2. Industrial Codes and Standards, the Universal Language. Think of it this way. Without a universal language, a process plant would be a chaotic, incredibly dangerous puzzle. Safety and consistency are just completely impossible without strict adherence to international engineering codes. If an EPC engineer sitting in Houston is designing a plant that's going to be built over in Dubai, they absolutely need to know they are speaking the exact same mechanical language. No room for translation errors here. Understanding exactly who writes that language is a non-negotiable prerequisite, especially if you're gearing up for a plant design interview. So let's look at the heavy hitters. First up, you have ASME, the American Society of Mechanical Engineers. Knowing your ASME B31.3 for process piping or B31.1 for power piping is absolutely mandatory for survival in this field. Then you have ASTM, which dictates the standards for your actual physical materials. We've also got API, the American Petroleum Institute, and ISA, which gives us the exact precise symbols we need to draw our instruments. You really have to know these organizations inside and out. To give you a sense of the sheer scale we're talking about, the American Petroleum Institute alone has developed over 800 consensus-based standards since they were established way back in 1919. Over 800. And listen, these aren't just polite suggestions. These are rigorous, uncompromising rules designed specifically to enhance operational safety and environmental protection across the entire globe. Section 3. Decoding PFDs and PNIDs, the plant storyboard. Okay, long before a single piece of steel is ever cut, these massive facilities are mapped out using two vital documents. First is the PFD, or Process Flow Diagram. This is your conceptual bird's eye view. It's simplified. It shows the sequential steps, inputs, and outputs. But then you step it up to the P&ID, the Piping and Instrumentation Diagram. This is the complex, highly detailed graphic that shows exact interconnectivity, safety schemes, and control mechanisms. It is the core storyboard of your entire facility. But here is a really vital secret of the trade. A P&ID actually can't show every single detail, because if it did, it would turn into a cluttered, completely unreadable mess. So to get around that, they rely on three critical support documents to hold all the nitty-gritty specifications. You have the PMS for your nuts, bolts, and gaskets. You have the EIS, which holds the extensive testing codes and material guarantees. And finally, the FRS, which details exactly how the whole system communicates and functions. Now, to actually sit down and read a P&ID, you've got to master the ISA S5.1 standard. Think of this as your visual grammar. It's a consistent, system-independent way of communicating everything about the instrumentation using very specific graphical elements. If you don't know this standard, I promise you, a P&ID is just going to look like a bunch of random circles and lines scattered across a page. Memorize these shapes. They are your new alphabet, and you're going to use them constantly in CAD and 2D drafting. A simple circle? That means you're looking at a discrete individual instrument. If that circle is inside a square, well, now it's a shared display or control. A hexagon indicates a computer function. And what about a triangle inside a square? That is your programmable logic controller, or PLC. Just by glancing at the shape, you instantly know the device category. So what goes inside those shapes? Letters, of course, and they are defined precisely by that ISA standard. The first letter tells you the actual variable being measured, so F for flow, T for temperature. The succeeding letters tell you the function, I for indicator, R for record. Put it all together, and a circle with FI inside immediately tells the operator they're looking at a discrete flow indicator. It's an incredibly elegant, efficient visual language once you get the hang of it. Section 4. Instruments, valves, and equipment. The physical hardware. All right, let's talk about valves. Valves are essentially the traffic lights of your piping system. They regulate, direct, or completely stop the flow of fluids. But a valve isn't just a valve. You have to specify the exact right type for the job. A gate valve is fantastic for completely stopping flow, while a globe valve is much better for regulating it. You also have check, ball, plug, and butterfly valves. In the real world, picking the wrong valve doesn't just cause a little inefficiency. It can lead to catastrophic pressure failures. Beyond the pipes and valves, your layout also has to account for massive pieces of industrial equipment, and this is broadly categorized into two main types. First, you've got static equipment, basically things that don't move. This includes massive storage vessels, heat exchangers that transfer thermal energy, and those towering distillation columns. Second, you have rotary equipment. These are the things that spin and do the heavy lifting, like pumps moving liquids, compressors handling gases, and massive turbines. Section 5. Isometrics and stress analysis, the final execution. Welcome to the world of isometric drawings. This is where those flat 2D concepts become highly accurate 3D representations. These drawings translate the P&ID and the general arrangement plans into a format packed with exact dimensions, detailed callouts, and specific symbols. But most importantly, an isometric drawing generates the BOM, or bill of materials. This is your exact material takeoff. Literally, every single pipe, flange, and bolt that is required for actual construction is listed right here. Now, here is something that is so often overlooked by beginners. You can't just float tons of metal filled with highly pressurized, boiling liquid up in the air. You must design and select the correct physical supports. You have resting supports taking the vertical weight, guide supports that allow for specific movement, anchor supports locking the pipe completely in place, and hanger supports suspending them from above. Getting this part wrong is a classic root cause for industrial accidents, where pipes will literally rip themselves apart just through thermal expansion. And that brings us to the final workflow of a piping engineer. Step 1. You lock in the equipment layout and the exact orientation of all the nozzles. Step 2. You draft those hyper-accurate piping isometric drawings we were just talking about. And step 3. You perform static pipe stress analysis. You mathematically prove, using specialized software, that those pipes are not going to break under the stress of gravity, internal pressure, and extreme temperature changes. Which leaves us with one final thought to consider. The stakes in piping design and drafting are just incredibly high. A single misread ISA symbol, the wrong ASME code, or a failed static stress analysis can literally bring an entire multi-million-dollar refinery to a catastrophic halt. The precision you bring to these documents forms the very backbone of industrial safety. So ask yourself, are your blueprints truly ready for the real world? For those of you looking to build a serious career in this industry, keep reviewing those codes, master your P&IDs, and never stop learning. Thanks for joining me on this explainer, and I'll catch you on the next one.